Welcome to the Church of Logic. I'm your host, Cody Rue. Last time we talked about the completeness theorem, and this time we'll talk about one of its more interesting consequences, the compactness theorem. So, the completeness theorem says, in one of its forms, that if a theory is non-contradictory, if it doesn't prove false, then it has at least one model. All right, great. So what can we do with this? One way is to kind of understand what it really means to be able to prove false, right? So it's important to remember that proofs only involve finite amounts of axioms. Indeed, finite amount of everything, right? The statements in a proof, are part of this finite tree, and so only a finite number of statements appear in the proof. And I think there's a lot of things that you can say philosophically about this, but one thing you can certainly say is that if you have an infinite number of axioms, it doesn't really matter, how to manipulate that. I'll talk maybe about this a little bit more when we go into Gödel's theorems. But, there's no real objection to having an infinite number of axioms. But if you carry out a proof using a theory with an infinite number of axioms, what is definitely true is that you've only used a finite number of axioms to finalize that proof, right? So say if you prove that, in arithmetic, there's an infinite number of prime numbers, right? Infinite number of primes, very standard theorem. Arithmetic, classical arithmetic is typically described with an infinite number of axioms. But it turns out that you only need a finite number of those axioms to prove this theorem, all right? So one might say, okay, well, what axioms do I actually need to prove this? And, there's an interesting field of mathematics that tries to understand, exactly how much of arithmetic do I need to prove all these different theorems? All right, so getting back to the completeness theorem and the compactness theorem, the compactness theorem observes that if you have an infinite theory and each finite subtheory is consistent, right? If each finite subtheory has a model, all right? Well, soundness certainly says that all of those finite theories can't prove false, right? That's what soundness says. So each finite theory can't prove false because it has a model. Now take the infinite theory, that all of the axioms together. Well, suppose that theory doesn't have a model, all right? It has no models. The completeness theorem says that infinite theory must be able to prove false. You must be able to derive a contradiction from that infinite theory. But if you look at that proof, it only involves a finite number of axioms. But we just said as our precondition that every finite number of axioms can't prove contradiction. Okay, so it's not possible to prove false from that infinite set of axioms because we've assumed that every finite set can't prove false. All right, and now the completeness theorem says, hey, that means this infinite set of axioms also has a model. All right, this is kind of miraculous because it's saying that if you can build a model from a finite set of axioms, then you can take them all together and glue them into this model that includes everything, right? Now, note that I didn't say each particular, a set of finite axioms, and each of them has a model, and then I can just take the union. It has to be, I take an infinite theory, every finite set of that infinite theory, all right? Every possible finite set needs to have a model, all right? So there's a slightly subtle point here, which is I don't get to choose how to partition my infinite theory into sets of models, right? I have to take any possible subset of that theory and show that it has a model. And if I can do that, then I can glue all these models together, build an infinite model for the infinite set of axioms. All right, so why is this cool? Well, here is, in my opinion, one of the cooler applications, but there are tons of others. And in fact, it's very easy to Google like applications of the compactness theorem and get a huge list of like really cool applications. So it's possible to axiomatize geometry, it's possible to axiomatize arithmetic, and in particular, it's possible to axiomatize the real numbers, right? You can axiomatize, what it means to be, to multiply, to divide, to add, to be a real number between 0 and 1. You can even axiomatize, what it means to be the square root of 2. So there's this very classical, well-known axiomatic system that just describes the real numbers, and where you can talk about, the field elements, the order between them, and you can even talk about, solutions of polynomials. You can even say, oh, if a polynomial has an odd degree, then it has at least one solution. Okay, so this theory is typically called real closed fields, and it's kind of an important theory because you can carry out a lot of geometry in it. And okay, so this theory is reasonable and it's intuitive and it kind of looks like what you expect it to look. Here's something you can do. You can say, okay, I'm going to take this theory and just add a constant, right? I'm going to call it epsilon, all right? Add this constant epsilon to my logical theory, all right? And so far I haven't said anything more. Epsilon has no properties particularly, and so that theory is consistent. You can just, say, okay, well, epsilon maybe is 1, or we don't know. And that is certainly a model of my theory where I just added this constant and did nothing. But I can also start to constrain epsilon. I can say, okay, well, epsilon is actually positive. It's strictly greater than 0. And it's also strictly less than 1. Okay, well, that still has a model. I can take epsilon is, 1/2, say, right? That's still a consistent theory. But then I can start adding more and more axioms to say, oh, actually, epsilon is just still greater than 0. It's still less than 1. Oh, but it's also strictly less than 1/2. And then I can just take the infinite set of axioms that say, oh, epsilon is less than 1/4, epsilon is less than 1/8, epsilon is less than 1/16. And I can keep adding that infinite set of axioms that keep making epsilon smaller and smaller. And I also keep the axiom that says epsilon is strictly greater than 0, all right? It's not 0. Here's the cool observation. It turns out that if I take any finite subset of real closed fields plus all of these constraints on epsilon, making it smaller than 1/2, 1/4, 1/8, that set of axioms is consistent. You just take the model that says, okay, well, it's just the reals, and I interpret epsilon as being smaller than the smallest axiom that bounds epsilon. You know that because you're only looking at a finite set of axioms, there's going to be a smallest constraint, like, epsilon less than 1/64th, right? And then you just take, oh, epsilon equals 1/65, and that satisfies the model. All right, great. So you have a model for all these finite subsets where epsilon is just this like kind of small number, and each different model is going to have epsilon being bigger or smaller depending on, which axioms you kept. The compactness theorem says, oh, actually, there's a model with all these axioms together. But hey, guess what? That means epsilon cannot possibly be larger than any fraction you could name. Epsilon cannot be larger than 1/64. It can't be larger than 1/256, right? It can't be larger than any of those because you've added all these infinite sets of axioms. So in this model, and again, we've proven that this model exists. We haven't really described it very concretely, but we know that epsilon has to be smaller than all these explicit fractions. But we also know that epsilon has to be greater than 0 because that's one of our axioms. And so the compactness theorem basically gives us this model that we don't really know anything about, except that it has all the axioms of the reals, the real closed fields, plus this magical epsilon that must be smaller than every fraction we can name and greater than 0. It turns out that this epsilon is really what you want to call an infinitesimal, something that's bigger than 0 but smaller than every fraction we can name. And then you can start writing down equations like saying, hey, what is, the value of a polynomial at a point plus that epsilon, right? And how is it different than the value of a polynomial at that point? And you'll find that, hey, it turns out that working with these infinitesimals is really the way, geometers and analysts did calculus in the 17th century, right? This is how Leibniz conceived of the real numbers. He had this notion of infinitesimals, which, in the 19th century, people were like, oh, this is bogus, this is unrigorous. But now in the 20th century and the 21st century, we find these really powerful ways of making these reasonings consistent by saying, hey, if you can't build an inconsistency in this kind of finite way, then you can never build an inconsistency at all. So this tool is just magical. And I invite you to Google the Axe-Grothendieck theorem to see that actually this tool is so powerful that you can prove these really cool modern theorems in abstract algebra just using the compactness theorem and kind of the power of classical logic and the completeness theorem. All right, see you guys next time.